Hello, we are doing a discrete mathematics and its applications problem. This is written by Kenneth Rosen. I'm using the 7th edition, so I am in chapter 5.1, question 35. If you're using a different edition, this might be a different chapter number and a different question number. What we are trying to show today is that n squared minus 1 is divisible by 8 when n is an odd positive integer. So let's start real quick with what it means to be divisible for an integer. So division of integers, let's say I have x divides y, and this slash is called division, or more appropriately, divides. So we say x divides y. Now we mean that x divides y evenly, and x and y here are integers. The fancy z is the set of integers. E means element. So x and y are elements of the set of integers. So what does it mean that x divides y? It means that I can write y as a multiple of x. So in other words, y will equal x times some other integer. That's what it means to divide. So when we say that n squared minus 1 is divisible by 8, we mean that we can write n squared minus 1 equal to some multiple of 8. That would be our goal. Now, let's look really quick at the question. We're trying to prove that n squared minus 1 is divisible by 8. Nothing wrong there. When n is an odd positive integer. So this is a bit problematic because when we do induction, essentially induction is like dominoes. If I have a bunch of dominoes and I assume that, say in this case, that everything up till this particular integer is divisible by 8, n squared minus 1, that the next case, if I prove that, then no matter where you start, I've proven the next case. So it's sort of like a domino falling. This one hits this, hits this, hits this, hits this. So we need consecutive numbers. That's why induction works over natural numbers, 1, 2, 3, or integers, 0, 1, 2, 3, positive integers. So when we have n is a positive odd integer, we have a gap, right? So this would work for this, but not this case, this, but not this case. So we need to fix that. We figure out a way in which we can prove this by induction. And so what we're going to do is we're going to have what we're going to say is a definition. An odd integer is 2 times some integer plus 1. I'm using k just as any integer, where k is an integer. And an even integer is, say, 2m, where m is an integer. So these are definitions. This is how we define odd and even integers. So we can do the same here. We can define n. So let's do that. But let's first start our proof, because this will have to be part of the proof. We'll say by induction. And first we're going to say let n equal, so n is our odd integer, so we can define it because we know what an odd integer is. Let's use m. So 2m plus 1 for m greater than or equal to 1, because we need this to be odd positive. And so when m is 0, we get 1. When m is 1, we get 3. When m is 2, we get 5, and so on. So this definition of n, 2m plus 1 will now range over the integers, mainly m. So now the induction is on m. Let me write that, on m. So I hope that's clear. We need to redefine n because n is every other integer. It's odd, so it's 1, 3, 5. We can use the definition of an odd integer, rewrite n, where m is now 0, 1, 2, 3, 4. And so it's consecutive. And now we can do induction on m. So the base case here will be when m equals 0. But what are we proving? So let's remember that we are trying to show that n squared minus 1 is divisible by 8. But now we've redefined n. We say n is 2m plus 1. So what we are really trying to show now is I'm going to replace n squared with 2m plus 1. We are trying to show that 2m plus 1 squared minus 1 is divisible by 8. So we've changed the problem a little bit, and this is what we want to show. So for the base case, we're going to do m as 0. So m is 0. So we plug 0 into our 2m plus 1 squared minus 1. Again, that comes from this, which is 2 times 0, 0. 1 squared minus 1 is 0. Or, yeah, 1 minus 1 is 0. And 0 is divisible by everything. Let's look at, this is not really something you would need to do for this proof, but let's just look at what 2 is. So 2 times 1 plus 1 squared minus 1 is equal to 2 plus 1 squared minus 1 is equal to 3 squared minus 1 is equal to 9 minus 1 is equal to 8. So indeed, 8 is divisible by 8. If you need to convince yourself of more terms, try m2, m3, and so on. So the base case holds. Now let's do the inductive step. So here we're going to make an assumption, which we'll call our induction hypothesis. And we're going to replace m with k. So what we are assuming then is that 2 times k plus 1 squared minus 1 is divisible by 8. We're going to assume this is true for, again, k greater than or equal to 0. So 2k plus 1 is replacing n squared. So 2k plus 1 squared. Okay. This is the induction hypothesis. So let's write that, induction hypothesis. If you've seen any of my other induction proof videos, you know I like to write IH so I can write it into our proof so I remember that I use it. Again, this is all suggestions. You don't need to write everything that I write for your proof. All right, so that's the induction hypothesis. We're assuming that 2k plus 1 squared minus 1 is divisible by 8. This is the PK case, right? The statement K or P is what we're trying to prove, and K is the case. So this was P of 0. Now, what we want to show is the K plus 1 case, or P K plus 1. I like to write this out literally. it helps me keep track of where I want to end up. So I'm going to replace k in the induction hypothesis with k plus 1. It's going to look a little unruly, but it helps just to do it literally first. I'm replacing k with k plus 1 minus 1. And I want to show this is divisible by 8. Now, I'm not assuming this is true. This is what I want to show. This is my assumption. All right, so we're going to take the 2 times k plus 1 squared minus 1. And we'll take a look at this. We'll do some algebra or some just basic arithmetic. And we're going to try to show that this is divisible by 8. In other words, that the pk implies pk plus 1, which is the conclusion of our proof, like any induction proof. Okay, so let's distribute this. If you need some refresher on multiplying polynomials, we have a video lecture series of college algebra. You could look at that and get familiar with polynomial multiplication. All right, so we have 2k plus 2 plus 1 squared minus 1. Now, you've learned in algebra, and perhaps just out of the math explorations, that you want to combine like terms. So 2k plus 3, square it, subtract 1. Let's resist that urge here. We want to use the induction hypothesis. To use the induction hypothesis, we want to be a little bit clever. We want to remember what we have assumed 2k plus 1 squared minus 1 is divisible by 8. So what I'm going to do here is I'm going to just group this a little bit differently. So I'm going to say 2k plus 1 plus 2 squared minus 1. Now 2k plus squared, or 2k plus 1 squared is what we want to end up with here. Just to make this a little bit cleaner, I'm going to let p equal 2k plus 1. Now, the reason I don't do that is because I want to square it. And if I can do this, it'll look a little bit cleaner if I write it like this. So I'm replacing 2k plus 1 with p. And you don't have to do all these steps. I'm just trying to illustrate. And hopefully people will understand. And you can write a more concise proof. So now I'm just literally looking at what this is. That's p plus 2 times p plus 2. And if we do FOIL, again, polynomial multiplication review. So that's p squared plus 4p plus 4. And we're subtracting 1. All right, so let's remember what p is here. P we said was 2k plus 1. So now I'm just going to replace it in there again. 2k plus 1 squared plus 4 2k plus 1. I want that to be a little bit clearer. Plus 4. And minus 1. Now, I probably didn't need to do that bracket, but let's just write this out. 2k plus 1 squared. Now, I don't want to square that because I know my induction hypothesis says I have 2k plus 1 squared minus 1. Well, I have a minus 1 here. Let me write it this way just to remove the brackets. And again, resist the urge to take 4 and subtract 1. Instead, I'm going to group it so that I have my induction hypothesis. So I get 2k plus 1 squared minus 1 plus 4 2k plus 1 plus 4. All right. So now it should be somewhat evident that grouping it this way was advantageous, because when I multiply out this second term here and add 4, I get 8k plus 4 plus 4. So that is 2k plus 1 squared minus 1 plus 8k plus 8. Now I'm going to look at this first term, because by the induction hypothesis, by IH, we said that 2k plus 1 squared minus 1 is divisible by 8. That means we can write 2k plus 1 squared minus 1 as a multiple of 8. So let's do that. So that means that 2k plus 1 squared minus 1 is equal to 8. Now we need another letter. Let's use q for some q that ranges over the integers. So I can just replace this in here with 8q. So that means that that's equal to 8q, because again, it's divisible by 8, and I'm going to add 8 times k plus 8. Now at this point, it should be obvious that we should factor out an 8. Now what we get is q plus k plus 1. So what is q plus k plus 1? This is just an integer. Now we've used a bunch of letters here. I could replace k or q plus k plus 1 with another letter if we want to, and say let this is an integer, so let it equal t. And then t is an integer, because the sum and difference of integers is an integer. Just like if we multiply integers, it's an integer. However, if we divide integers, we don't always get an integer. So this means that this is equal to 8 times t. Now, what do we say about division? We said that if something divides something else, we can write the thing that's being divided as an integer multiple of it. So this means that, where do we start? 2k plus 1, or let me write the literal thing that we started with. So that was 2k plus 1 squared minus 1 is equal to 8t. Which means that 2k plus 1 squared minus 1 is divisible by 8. And that's what we wanted to show. Therefore, remember back to the beginning, we replaced n squared with what it means to be odd. So we'll just go back to the beginning, and we've shown that n squared minus 1 is divisible by 8 when n is an odd positive integer. And that's the proof. We'll say QED. Again, I prefer boxes. That's it. So the little trick here was, in the beginning, we had to rewrite what we mean by odd so that we can use induction, because otherwise we couldn't use induction. The dominoes won't fall when there's a gap between the numbers. 1 needs to proceed 2, needs to proceed 3, and we had 1, 3, 5, 7, 9, so on. So that's it. That's the proof. Like and subscribe if you can. Thanks for watching, and we'll see you next time.